Let's dive in. Today, we're about to uncover the hidden world that powers nearly every aspect of our daily lives. It's a world that's invisible to most of us, yet it's everywhere, embedded in the devices we use, the cars we drive, and even the appliances in our kitchens. Look around, your phone, computer, car, even your fridge, they all have a brain, a microchip, or CPU. These chips are the silent workhorses behind the scenes, making sure your messages get sent, your music plays, your navigation works, and your food stays fresh. They're the reason your smart TV can stream movies, your smartwatch can track your steps, and your voice assistant can answer your questions in seconds. These tiny silicon marvels are the engines of our digital world, performing billions of calculations every second. Imagine a city where every light, every car, and every building is perfectly synchronized. That's what a microchip does, but on a scale so small it's almost unimaginable. They process information at lightning speed, making split-second decisions that keep our digital lives running smoothly. Without them, we'd be stuck in the analog age. Remember rotary phones, static-filled radios, and televisions with just a handful of channels? That was life before microchips. Today, we have access to a universe of information and entertainment, all thanks to these tiny brains. At its core, a microchip is a complex circuit board shrunk to the size of your thumbnail, packed with billions of microscopic switches called transistors. Each transistor acts like a tiny gate, controlling the flow of electricity and allowing the chip to process information. The sheer number of these transistors is staggering. Modern chips can have more than 50 billion packed into a space smaller than your fingernail. These transistors, flipping on and off, are the ones and zeros of binary code, powering everything from simple math to advanced AI. Every photo you take, every video you watch, every game you play, it all comes down to these tiny switches working in perfect harmony, turning electrical signals into the digital experiences we rely on. The story of how these chips are made is a feat of engineering, combining physics, chemistry, and mind-bending precision. It's a process that pushes the limits of human ingenuity, requiring clean rooms, lasers, and machines that can manipulate materials at the atomic level. Every step must be flawless, because even a single speck of dust can ruin an entire batch of chips. We're talking about building structures smaller than a virus, in facilities cleaner than a hospital. The air inside these factories is filtered thousands of times to remove even the tiniest particles. Workers wear special suits to avoid contaminating the chips, and every movement is carefully controlled to maintain absolute precision. The journey from sand to CPU is a saga of purification, precision, and assembly. It all starts with ordinary sand, which is refined into ultra-pure silicon, the foundation of every microchip. This silicon is then sliced into thin wafers, which become the canvas for billions of transistors. In this video, we'll pull back the curtain on this process, step by step, from raw materials to the finished product. You'll see how cutting-edge technology and human expertise come together to create the chips that power our world. We'll see how sand becomes ultra-pure silicon, how patterns are printed with light, and how billions of transistors are wired together. We'll explore the incredible machines that etch circuits just a few atoms wide, and the rigorous testing that ensures every chip meets exacting standards. So grab your safety glasses and put on your clean room bunny suit. We're about to enter a world where science fiction becomes reality, and where the future is built one atom at a time. Let's explore the world of microchip manufacturing. Get ready to witness the incredible journey that transforms simple sand into the brains of our modern world. A journey that shapes the technology of today and the innovations of tomorrow. Every microchip, the heart of our modern digital world, begins its journey with a single unassuming element: silicon. Silicon is the second most abundant element in Earth's crust, making up about 28% of its mass. It's found almost everywhere, but especially in the form of sand and rocks. This humble element is the foundation of all the technology we rely on, from smartphones to satellites. Silicon is most commonly found in beach sand and quartz. If you've ever walked along a beach or picked up a piece of quartz, you've held the raw material for the world's most advanced electronics in your hand. But while it's plentiful, not just any sand will do for making microchips. You can't simply scoop up beach sand and start making chips. The silicon used in microchips must be incredibly pure, 99.9999999% pure to be exact. That's just one atom of impurity for every billion atoms of silicon. Achieving this level of purity is a scientific and engineering marvel. The process begins by taking high-purity quartz and melting it in a powerful electric arc furnace. At temperatures above 2000 degrees Celsius, the quartz breaks down and the silicon is separated out. This produces what's called metallurgical-grade silicon, which is still not pure enough for electronics. To reach the required purity, the silicon undergoes further purification. It's often converted into a gas, then filtered and condensed back into solid form as electronic-grade polysilicon. This step removes nearly every trace of unwanted elements, leaving behind silicon so pure it's almost unimaginable. But purity isn't enough. For microchips, we need a perfect crystal structure. The purified polysilicon is melted in a crucible, and a tiny seed crystal is carefully dipped into the molten silicon. Slowly, the seed is pulled upward and rotated, allowing a flawless cylinder of silicon, called an ingot, to form around it. This is known as the Czochralski process, and it's a delicate dance of temperature, timing, and precision. The Czochralski process demands extreme precision. Even the slightest imperfection or contamination can ruin the entire ingot, potentially wasting thousands of future microchips. Technicians monitor every detail, ensuring the crystal grows perfectly, atom by atom. The result is breathtaking, a shimmering 2-meter-long silicon ingot. This cylinder is one of the purest and most perfect structures ever created by humans, a testament to our ability to shape the elements of nature for our needs. What began as ordinary sand, something you might find between your toes at the beach, has been transformed into a flawless silicon crystal. This transformation is nothing short of alchemy, turning the mundane into the extraordinary. This remarkable process forms the foundation for every microchip, every processor, and every memory chip in existence. Without this transformation, modern electronics simply wouldn't be possible. Next, this perfect ingot will be sliced into ultra-thin wafers, each one destined to become the canvas for millions of microscopic circuits. The journey from raw material to high-tech marvel is only just beginning. The story of silicon is a story of transformation, of how we take something common and, through ingenuity and precision, turn it into the backbone of our digital age. The journey from sand to silicon is just getting started. In the next chapter, we'll follow this silicon as it enters the next stage of its journey, moving ever closer to becoming the brains of the devices we use every day. Let's see what happens next. Imagine a flawless cylinder of pure silicon known as an ingot emerging from the heart of a high-tech factory. This ingot, often weighing hundreds of kilograms, is the result of a painstaking process that transforms raw sand into one of the purest substances on Earth. It's like a giant log, but instead of wood, it's a shimmering, metallic crystal, destined to become the backbone of modern technology. But before it can power our devices, it must be carefully sliced into thin, precise discs called wafers. Using a diamond-tipped saw, engineers cut the massive ingot into wafers that are less than a millimeter thick. This process requires incredible precision, as even the slightest error can ruin an entire batch. The saw itself is a marvel, embedded with industrial diamonds to ensure each slice is perfectly smooth and uniform. Each wafer must be exactly the right thickness to support the complex circuitry that will soon be built upon it. Once cut, these wafers are stacked and inspected. Each one serves as the foundation for hundreds, sometimes thousands of microchips. These chips will eventually find their way into everything from smartphones and laptops to cars and medical devices, making the humble wafer a silent hero of the digital age. However, the freshly sliced wafers are far from perfect. Their surfaces are rough, covered in microscopic grooves and imperfections left by the saw. Before any circuits can be built, these surfaces must be polished to a level of smoothness measured in atoms. This is where chemical-mechanical polishing comes in. Using a combination of abrasive slurries and precise mechanical action, machines buff the wafer until it gleams like a mirror. This mirror-like finish is absolutely essential, as even the tiniest bump or scratch could disrupt the delicate patterns that will soon be etched onto the surface. The entire process takes place in ultra-clean rooms, where the air is filtered constantly to remove even the smallest particles. A single speck of dust, invisible to the naked eye, could destroy a chip worth thousands of dollars. That's why workers wear full-body suits, often called bunny suits, to prevent any contamination. Every movement is carefully controlled, and the environment is monitored around the clock to maintain absolute cleanliness. The result is a flawless 12-inch disc of polished silicon, so smooth and pure that it reflects light in dazzling rainbow patterns. This wafer is now ready to become the canvas for the next stage of chip creation. On this pristine canvas, engineers will soon build the intricate circuits that form the heart of a CPU. Every transistor, every connection will be crafted with atomic precision. Hundreds of chips will be created on a single wafer, each one a tiny marvel of engineering. These chips will power the devices that connect our world, from the smallest sensors to the most powerful supercomputers. With the wafer prepared, the stage is set for the real magic, building the circuits that will bring silicon to life. The next steps will push the limits of science and engineering. Let's dive deeper and see how this incredible transformation unfolds, step by step. Now we create billions of transistors on the wafer using photolithography, painting with light. The wafer is coated with a light-sensitive photoresist, then spun to form a thin, even layer. A machine called a stepper shines ultraviolet light through a mask, projecting a circuit pattern onto the wafer. The exposed photoresist changes chemically, creating a stencil of the circuit. After developing, the pattern remains ready for etching. This process is repeated for each layer, building up the chip's complexity. Photolithography is the heart of chip making. Printing features thousands of times thinner than a hair. Next, we'll carve these patterns into silicon. With our photoresist stencil in place, it's time to etch, removing material from unprotected areas. Using plasma etching, we carve deep, precise trenches into the silicon. After etching, the photoresist is stripped away, revealing the new features. But to make transistors, we need to control electricity flow, so we dope the silicon. Ion implantation shoots dopant atoms into specific regions, changing their electrical properties. Masks block ions from certain areas, creating the transistor's source, drain, and gate. The wafer is then heated to activate the dopants and repair the crystal. Etching and doping are repeated for each layer, building the chip structure. These steps turn blank silicon into a dense forest of transistors. Now we need to connect them all. Modern CPUs are built in layers, like a skyscraper, not a single floor. Each layer is separated by an insulating film, then connected by tiny vertical tunnels called vias. Photolithography and etching create these connections, forming a 3D matrix. Next comes wiring. Copper is used for its superior conductivity. The Damascene process fills etched trenches and vias with copper via electroplating. Excess copper is polished away, leaving only the embedded wiring. This sequence, insulate, etch, fill, polish, is repeated for up to 100 layers. The result, a dense, intricate web connecting billions of transistors. Layer by layer, the chip's complexity grows. The wafer now holds hundreds of complete, interconnected CPUs. Time to test them. Test. After weeks of work, the wafer is ready for testing. Automated machines use probe cards with microscopic needles to test each chip's basic functions. Defective chips are mapped and marked for discard. The percentage of working chips, yield, is crucial for cost and efficiency. Once tested, the wafer is mounted on sticky film and diced with a diamond saw. Each tiny square is a raw, unpackaged processor. Only the good chips move on. Dicing separates hundreds of CPUs from a single wafer. The next step, packaging. Let's see how these fragile dies become the CPUs we know. The raw silicon die is delicate, it needs protection and a way to connect to the outside world. Packaging starts by mounting the die onto a substrate, a mini circuit board. Tiny wires or solder bumps connect the die to the substrate. Wire bonding for simple chips, flip chip for high-performance CPUs. Flip chip allows more connections and better performance. The assembly is encapsulated in a protective casing, often with a metal heat spreader for cooling. The heat spreader draws heat away, preventing damage. The finished package is what you recognize as a CPU. Packaging is critical for power, cooling, and communication. Now the chip is ready for its final tests. Only the best make it to market. Let's see how they're chosen. The packaged CPU faces one last round of rigorous testing, final test. Each chip is placed in a test board and pushed to its limits. Every function, instruction, and memory is checked. Stress tests at different voltages and temperatures ensure reliability. Chips are binned by performance. Faster ones become premium models, others are sold as budget options. Any chip that fails is discarded, no room for error. Passing chips are laser etched with model numbers and branding. They're packed in anti-static trays and shipped worldwide. From there, they're installed in computers, servers, and countless devices. That tiny piece of silicon, once sand, is now the brain of our digital world. The scale and precision of this process is staggering, and it all starts with a grain of sand.